Okay, this is lecture 20. Um, Technically Monday's lecture, but they're going to blur together between Monday and Wednesday as I'll be posting several videos. This one won't probably last the full 50 minutes, so I'll be adding an additional one. Basically, what I want to do is go through everything of 16.1 and part of 16.2, and then save the more challenging problems for when I'm back on Friday and next Monday. So hopefully you've looked at, excuse me, hopefully you've looked at chapter 16.1. Now I realize there's not a whole lot of theory, but there's enough to give you kind of an idea of what we're looking at in this chapter. And you may have noticed the pattern of the previous lecture in terms of the way we solve problems is looking at these simple F equals ma problems and really breaking them down to summing the forces in direction, summing moments, and using the fact that the acceleration of the center of gravity adds an aspect to the problem that we before which have never considered. So if we think about a rigid body, for example, and here this is just a free body diagram, kinetic diagram I'm showing. To the left is what it actually looks like. And here you have two linkages, and each linkage is equal in length. And so the question is if you were to release that linkage from rest, then it would it would start to move in and down to the left because it's constrained by CA and DB. And if we look to the right, we can see this is what the free body diagram would look like for the disk itself. It has a center of gravity where weight is always pointing straight down. And then it has the forces from AC and DB pointing up at 75 degrees. And then the kinetic diagram simply has MA pointing in that direction. And that direction is, of course, perpendicular to AC and BD. So in this problem, we can see that linkages AC and BD do rotate uh, and have angular acceleration, but the disk itself does not. It only translates. So that leads us into our next example where we have something similar. We have our three-sided shark tank, and each of a mass of 3 kilograms, and they're welded together, and then they're pinned at these connection points EB and FC. Now, if we release it, and one of the things in the problem I haven't told you, and in the book it would, but the center of gravity of this is unknown at this point. So we have to figure out where that center of gravity is. And actually, this is the wording from the book. It doesn't tell you, but we know that when this thing is released, it's going to fall to the right and down. And so we have to identify what is the actual direction of MA. So think about it. If you guessed it would be down to the right at 40 degrees, then you're correct, which would be perpendicular to linkage EB and FC. Again, down to the right at 40 degrees from the horizontal. So the first thing we're going to do in this is because we know that MA, the mass times acceleration of the center of gravity, is going to be important. We have to figure out where it's located so that we can determine what moment it creates. So looking at my diagram here, we have weight in the middle. We have 50 degrees, 50 degrees. Now, this height of 150, I've already determined that ahead of time, but let me show you where I got that from. So we know that y bar is equal to what? It's equal to the sum of the masses times their lengths all over the sum of their masses, right? Just like we found in statics. So if I use this down here as my y equals 0, then y bar is essentially equal to 3 kilograms, because remember each link mass equals 3 kilograms. Each link times its length, which is 225 millimeters, And again, for centroids, we can just use the millimeters. And then 3 times 225 plus 3 times 0. Right? Now, where do I get that from? Well, I know that the height of this, if we look back at the picture, it was 450, right? So if you go back to the picture, you'll see that this height was 0.450. Each link was 450 millimeters long. So the centroid of each in the y direction would be here, here, and here, which would be right through our datum, y equals 0. Hence, 3 times 3 kilograms, 3 kilograms, 3 kilograms times 0. And then divide that all by the total mass, which is 9 kilograms. So when the smoke clears, I get 150 millimeters. Okay. So now I know the height where this exists. That's 150 millimeters. Okay. That's the first part. Now, in terms of solving from there, let's look at the acceleration. Now, here's G, and if we see that this is 50 degrees, we can see that this is going to be our direction of MA. Now, if we think about it, this is what our vector looks like. This is mg, right? It always has to point straight down. So that's going to be the weight of the object, the total weight of the object times gravity. And then ma, consider that your acceleration in the tangential direction. And this here on this side of it would be your acceleration in the normal direction. Now, what we know is that at the point at which it's released, omega is 0, right? Because we're looking at a instantaneous time. And so there's no time for it to move, omega is 0. But there is a tangential acceleration. That tangential acceleration is due to ma at that angle. Okay? So what we can do then is we can say, how do we determine the acceleration? Well, the acceleration is just going to be that amount of ma that goes in that direction. Or if you think about it, it would be mg times cosine of 50 degrees, which is the same as mg sine 40 degrees, right? Same thing. So if I think about, and again, I don't have to worry about the masses here because I'm just looking at just the acceleration. The acceleration is really just g times cosine 50. So that turns out to be the acceleration to the center, which is what our little bar here represents, is 6.306 meters per second squared. And I always encourage you to carry a few extra sig figs and then round when you get to the end. Okay? So now we have that. So now we want to think about now that we have that acceleration overall, we have to think about what is that acceleration in terms of x and y. So we have effectively an acceleration that goes down like this, okay? And it's going down still at 40 degrees. So that's our MA. So we can kind of think of this as that's our MA in the X, and this is going to be our MA in the Y. Okay? So what that means is that my acceleration X is equal to A cosine 40 degrees. My acceleration, sorry, getting off the page, acceleration in the Y is equal to A sine 40 degrees. All right. So far so good. If you're not clear on that, I would pause for a moment, walk through what I did, but hopefully this is pretty clear. So to reiterate, and you can fast forward this if you already understand, but to reiterate, we have this, this, and that. Okay, so that's my MA bar, and that was based on this, where that's my hypotenuse, and those are my two sides. So that's my normal, and that's my tangential. Okay, so now we have those. So now it becomes very similar to a problem that we would have done before, because again, if we go back to what we're looking for the force or normal force in BE and the normal force in CF, right? That's what we want. So remember that look at it like this. That's BE and that's CF. Sorry if I skipped that. Okay. That's what we want. We want to know what those two are. Now, we could have found them from statics, summing the forces in the y to zero, and we would determine that. But if you think about it, if this thing's going like this, then the sum of the force is going to be transferred between the two because of the fact that it's falling away. Okay, and you can think about which one's it going to be. Is it going to be this one or this one that's lessened by the fact that it's doing that? So make your prediction and then let's see what we get. So from there, we can then say, I'm going to pick B as my moment point. So I'm going to say the sum of the moments about B equals the sum of the moments about B effective. All right. So that's and so the way that would look is it would say the sum of the moments about B equals, and you wonder like, well, where's the I alpha plus MAD come from, right? Well, in a sense, we can think of it as the angular acceleration in this case is going to zero because, again, we do have an acceleration in that direction, but there's no rotation. So this whole thing is translating, right? Not rotating. So this term isn't needed. All right. So all we really have is MAD when we sum our moments. And that's what this effectively is, the effective. So you can kind of think of it as the sum of the moments of B equal MAD. Okay. I know that might seem weird, but bear with me. So let's go ahead and just write out what we have. So we know the force of CF, right? And that's going to be taken at this point here. So the only part of it that's going to count is the vertical, since the horizontal goes right through the point B. So force CF sine 50 degrees. And then how far is it? It's going to be 0.45 meters, right? Because this distance is 0.45. So there's that first part. And then that's clockwise, or that's counterclockwise. So again, we're following the convention of positive. And now we have to subtract because we have our center of gravity, right, up here. And that's going to be minus 9 total mass times gravity, and then times 0.225 or half of that width. Okay. So that's the only force we have acting. So now we have to look at it as that's going to equal then the two accelerations, right? Because we have, like we found earlier, we have an acceleration that way and that way. And so this acceleration here, which was our A bar X, has this height, which is 0.15. And that's why we needed that height before. Whereas this here, we know that that's distance is just going to be the 0.225 because it sits in the center. All right. So we have, let's go ahead and write it in. So we have what? we have minus 9 mass times 9.8. Okay, so that's our mass. And then um, times, oh, I apologize. I was looking at the wrong line. If I could edit it easily, I would. So forget that last thing. Uh, so what I have is minus, I'll just write it as MA bar, okay, times sine 40 degrees times 0.225. All right. And I know that this is, as I wrote earlier, AY. So that's my acceleration. I'm sorry. Uh, yeah, that's my AY. So A sine 40, and it's 225 because that's how far it is from this point here. So that distance to there. And then I have my other piece, which is minus, because, and the reason they're minus is because the moments are both clockwise, and that's going to be M A bar, and that's going to be times cosine 40 degrees, and then that's this side, so its distance is 0.15. Okay. So if you go in and we substitute A, right, we know A bar was 6.306, and we substitute in the mass of 9 kilograms, then you can solve. I'll leave that to you, F df, and that gives me 14.90 newtons, and that's in compression, pointing up, although we usually don't ask you this. And then if we want to know what the FB, not CF, I'm sorry, the other F, the FBE, then we simply sum the forces in the Y equal to 0. Because in this case, if we're looking at the force going straight up, we don't have to worry about any um, acceleration. Now, that might seem strange because of what we did earlier, because we did account for an acceleration in the Y, and that's true. But remember that once you find this, you know that the entire object has to still balance out in terms of force. What that means is that, yes, I have 14.9 going up in that direction, but I still have to balance it in equaling to 0 because the total mass of this can't be greater than the sum of these two. The only thing that this falling does is distribute the mass between these two, or the force of reaction between these 2 points. But otherwise, the overall weight of this has to add to these two. Okay, that's why that's done that way. So FBE plus 14.90 minus 9 times 9.81. And again, here I'm doing sine 50 degrees because I'm looking at, again, this direction. So I'm saying that what is the weight in that direction? So using that, and that all has to be 0. And so what I find, though, is FBE is equal to 52.7. All right. So if you guessed that this side would hold the lion's share, then you are correct. Because as this falls away, it doesn't have to hold as much because it's literally going away from it. It's like if you were to hold something in your hand and then drop your hand down really quickly, the normal force in your hand would drop. Okay. And if you were to raise your hand really quickly, the normal force would increase. So hopefully that makes sense. I would, if it doesn't, go back review, but by all means, if there's something I missed in here, please ask in class or come to see me in office. All right, so let's go back to our slideshow. Maybe I could find it. Oh, there we go. All right, so let's look at another type of problem. Um, I think what we'll do is let's look at this one. And this one's very similar to what we did. Now here we have a cart being pulled by horse P, and you have a 1 meter rod that weighs 15 kilograms. And then you have a cart that weighs 30 kilograms. And you have a P force that's pulling it with 300 newtons. And sorry, that was left off there. So we have a force of 300 newtons or something along those lines. Find the exact number. No, it's actually 90 newtons. I'm sorry. So this is 90 newtons. So I would go ahead as practice, pause the video and draw the FBD and the MAD for these two as you would see them. And then when you come back, we'll go ahead and solve it. And if you can solve the whole thing using the techniques, more power to you. So the more you can do on your own, the better off you are. And here you have more time than you would in class. Let's go ahead and pause and then back and solve. Okay, so here's my drawing of this. Now, this is just a general drawing of what I have. Now, one thing we can figure out right away is that if we know that it's 90 newtons going to the right, and we know the total mass is 30 plus 15, then that's 45. So we know the acceleration is 2 meters per second squared. All right, so we found that out pretty quickly. One thing we want to do, and sorry, the drawing, you can see from the drawing that this is 30 degrees, and then this little angle here is 30 degrees. Now, what we're going to have to do when we solve this is we're going to have to figure out the normal angle to this. And so if you think about this is coming up, if we think about the normal angle, then it looks kind of like this. Sorry, it's a little put up there. So this is 30 degrees and that's 30 degrees. So if I dropped a vertical down to the horizontal line, this would be 60 degrees. But in terms of what the horizontal line is with respect to the incline, it's 30 degrees. All right. So that might help to draw this out and make sure you understand the trig and where the angles are so that when I write out the sum of the forces and I sum of the moments, you can see why I'm using the angles I'm using. Okay. So that's what it looks like. It started out like this here at 30. And then when we draw our FBD MAD, it just looks like this effectively. And so what I should probably draw is something like this. And then we know that this angle here is 30 degrees. Okay. So now, just like before, we want to figure out, in this case, the reaction, Cx and Cy. And so how do we do that? Well, we treat it like before. We say uh, this thing has an acceleration of 2 meters per second squared. So what would Cx and Cy be? They're going to be different than it was if it was in static equilibrium. We're also going to figure out what this force AB is, all of which would have been a very trivial statics problem from chapter 4. But let's look at it now in the dynamics viewpoint. I'm going to go ahead and so this is where if you want to pause and write out what you think it is. Moment about C. So I pick C. Why? Because it has two unknowns, just like in statics. We want to eliminate those. And then I have my force AB. So some of the moments about C, some of the moments about C effective. And what do I have? Force AB, sine 30, right? So I know that the vertical part of it, if I were to draw, would look like that. And there's my 1 meter. Okay. So I have FAB sine 30, 1 meter. So that side of it is 1 meter away. And then that's going to be minus the weight, 15 kilograms times gravity times cosine 30.5, right? Because that's this distance here, effectively. So this distance is 0.5 cosine 30 degrees. Okay, sorry, it's hard to read. So that's 0.5 cosine 30 degrees. That's what that says. Because this is also 30 degrees. Okay, so now we know that side, and that is that. So those are the only two forces we have, right? Gravity, the weight, center of gravity, and FAB, since those two are taken away from the moment. Then that equals, again, the moment created by the acceleration of the center of gravity. So that's just my max, all right? There's no may. So I have minus 15 times 2 times 0.5 times sine 30, right? And again, that's the distance. 0.5 sine 30 is the distance that the moment is that's created from here to here. So it's that distance, right? So that's creating a course, and it's negative because it's creating a clockwise moment. So once again, looking back at the original equation, we see that if you take some of the moments about the center of gravity, which is that, it equals I alpha. But since we're taking, without that, sorry, if we take the sum of the moments about C, then it's I alpha plus MAD, right? And so once again, combining this isn't rotating. So this MAD perpendicular is exactly this. It's the mass times the mass times gravity, sorry, mass times acceleration, I apologize, times the perpendicular distance, okay? So what we end up with is the force AB is 112.4 newtons. And if we calculate it from a static standpoint, it'd be 127.4. So we can see this less because as this pulls away, this thing wants to do what? It wants to go up. Now it doesn't actually get that. It doesn't actually have rotation because there's obviously still tension there. The only way to get rotation is if we accelerate it at a fast enough rate to basically make this force less than or equal to 0. Okay. And then the rest is just statics, right? We sum the forces in the x equal to max. Here, I'm sorry, this is just chapter 12 stuff. Negative cx plus fab cosine 60 equals the acceleration in the x times, I'm sorry, the mass times the acceleration. And so we get 26.2 newtons going the other way. And we know the sum of there's no acceleration in the y, so it's just cy plus the y component of fab minus the mass of 15 times 9.81 gives us 49.8. And that's pretty much it. So there are a couple of problems like this on your homework. I think with this, you should have no problem doing them. There's a couple others that are a little more challenging. They require some thinking out of the box in terms of solving multiple equations, but they're pretty much the same idea. They still follow the logic of sum of the moments equals sum of the most effective, and that you can use the I alpha plus MAD, and where I alpha disappears if there's no rotational acceleration. Okay, so let's look at the last problem for this. Okay, so here's another question. Now, here we have a link, BE, that's hanging. It has a mass of 5 kilograms, 1.2 meters long. And we're told the angle it hangs at, and we're told that it hangs by AB and DE. Now, in this case, we want to find what is the force P such that the tension in AB is 300 Newton and the tension in DE is 200 Newton. So what that means is that this is pushing on it. This is, again, not rotating, but translating, right? However, These ropes, though, at that instant are both rotating and translating. Well, they're just rotating. I'm sorry. So these are rotating. So they'll have an omega and an alpha, both of them, and the bar will just have a translation, if that makes sense. So think of it as just going from up, and I can show that on the paper. So let's go ahead and look at this one. So here we have, so you can think of it as it's hanging there like this, and as a result of P, it's going like that. So the ropes will have a motion like that, but this itself will just have a translation. So there'll never be a rotation about G. It'll just go like that. Okay? Now, so what do we have? We know that P, this is our free body diagram, which I'm sure you paused the video to draw because you're a glutton for practice. And what did we get? We got P equals 300 newtons, 200 newtons, respectively, at A, B, and DE. We know their distance, 0.4 meters. We'll need that later. We know this is 0.6 meters. That's 0.6 meters. We know that's the center of gravity there. We know the mass is 5 kilograms. We want to find P, omega, and alpha of A, B, and DE. They're going to be the same for both. So there's our acceleration in the y, acceleration in the x, because if the bar is doing this, it's going to be going both that way and that way. So translating in 2 dimensions. All right. Now, first off, we're going to figure out what P is. So we're going to sum the moments about G. Now, what's the sum of the moments about G, the center of gravity? It equals I alpha. But I just told you that if we're going about center of gravity, that's all we have. We don't have an MAD term. That's only if it's a point other than the center of gravity. But we know that this is only translating. So this goes away. So really, this equals 0. Okay. So what I can do then is I can say 200 newtons for this times what? 0.6 cosine 30 degrees. And that's just this distance like that. So there's my 0.6 cosine 30. And then I have, and this is positive because it's counterclockwise. And then I have A, which is clockwise. So it's going to be minus, clear 30 degrees, minus 300 times 0.6. And that's going to be cosine 30 also. All right. And then that's going to be plus P, which we're looking for. And P, of course, we know is just going to be this distance here. So that's going to be 0.6 sine 30 or 0.3. And all that equals 0. So we did do a sum of the moments about G equals the sum of moments about G effective, didn't we? It's just that if you do the sum of moments about G effective, there are no moments created about G because it's not rotating. Okay, so uh, and maybe I hope that doesn't confuse things more. Effectively, this works when you have a point when you're taking a point other than the center of gravity. Okay, otherwise, if you're taking something else about G, then all you have is this I alpha. All right. So I agree. I realize that is a little different than what we've done. So again, this stuff not trivial, but I think once it clicks, you'll see that we're kind of doing similar repetitions in our problem set, trying to not muddy it too much more. So when when the smoke clears, we end up with P equals 173.2 newtons. So now we have our value for P. All right. Now we also want to find omega and alpha. So how are we going to do that? Well, we'll do things like we would expect with MAX and MAY, we would just sum the forces into Y equal MA normal. Now, why can I do that? Because this is MAX, this is MAX, MAY, but from the perspective of the cable, all right, the cable's moving with respect to this force going up is a normal. I'm sorry, this acceleration going up is a normal. This acceleration going that way is a tangential. Well, what do we know about a normal? It's the same as r omega squared, isn't it? That's a normal, right? So if we go ahead and set that up, sum the forces in the y, what do we have? We have 300, making this positive, plus 200 minus 5 times 9.81, right? Those are all the forces in the y. And then that whole thing just equals m r omega squared, right? So ma, or mr omega squared. Well, we know that m is 5, and we know that r is 0.4, and that's omega squared, right? So if we solve, we get omega squared, and we don't know which direction it's going. So I'm going to put an absolute value there, and that's going to give me a value of 15.02. I'm sorry, not omega squared, omega. Omega is going to be 15.02 radians per second, absolute value. All right. And again, sum of the force in the y, 300, 200 minus gravity equals ma, where a is the normal acceleration because that's the direction of this. So as this rotates around, the acceleration of this rotation points back to the center. Hence, I substitute in this r omega squared r. All right. So you can probably see for yourself the next one, that's going to be tangential. So you should have no problem solving that for yourself, because for that, you know that if I sum the forces in the x equal to MA tangential, or MAY, A tangential is what? It's R alpha, right? So the bar has no alpha, but the cables do. And so what does that give me? It gives me P, that's the only force in the x, equals 5 kilograms, and that's going to be times 0.4 times alpha. Okay, just substituting that in. So 5 kilograms, 0.4 alpha, 0.4 alpha. So what's 5 times 0.4? It's 2. So I get 173.2 divided by 5 times 0.4, which is really just 2. So it's half of that. So that gives me 86.6 radians per second squared. Now, in this case, I do know it's going that direction, and that's because P is pushing there. All right. And I would probably guess that omega is also going that direction, but we don't know for sure. All right. Okay. So hopefully that makes sense. Hopefully you see how we use these simple relationships of m sum of the moments equals I alpha to solve these problems, even though they're slightly different. They all use the common way. All right. So this would be the equivalent of what I probably would have finished between on Monday, but I'm going to, since Wednesday, it'll be asynchronous also. There will be something else that I'll put up on Wednesday. And then on Friday, as I said, we'll go over some more complicated problems. All right. You guys have a good rest of your day, and thank you for tuning in.